Designing a unique ID generator. So in this part, we will try to design a unique ID generator. So to start with, what is a unique ID generator? A unique ID generator is a software tool or a program that generates a unique identifier or a unique key for a particular entity, such as a transaction, a product, or any other object that needs to be identified in a system. The generated unique ID is typically a combination of alphanumeric characters and is used to ensure that each entity is uniquely identified and tagged within a system. The purpose of unique ID generator is to ensure that every entity in a system has a unique identifier that can be used to reference it. This is important for a variety of reasons such as data integrity, security, and traceability. For example, a unique ID can be used to ensure that no two users have the same username or to track the progress of a transaction as it moves through a system. Unique ID generators can be implemented in many different ways, including through the use of random number generators, hash functions, or other algorithms that generate unique strings of characters. So exact method use will depend on the specific requirement of a system in question. In this section, we will uh, we have given we have been asked to system design a unique ID generator in a distributed system. So the first thought that might be to use primary key with the auto increment attribute in a traditional database to generate a unique ID generator. However, auto increment does not work in a distributed environment because a single database server is not large enough, and generating unique ID across multiple databases with minimal delay is very challenging. So that's why we have to come up with a design which can help us to basically generate unique ID in a distributed way. So that is pretty much on the intro part of a unique ID generator. Standing problem. In this part, we will try to understand our problem and establish a scope of it. So asking a clarification question is the first step to tackle any system design interview question or interview problem. So here is an example of a conversation between a candidate and an interview that should happen to understand this unique of designing this unique ID generation problem. So let's see how that conversation looks. Candidate, he asks like, what are the characteristics of a unique IDs? Interviewer, IDs must be unique and sortable. Okay. Then candidate asks, for each new record, does ID increment by one? Interviewer, the ID increments by time, but not necessarily only increments by one. IDs created in the evening are larger than those created in the morning on the same day. Okay. Candidate, do IDs only contain numerical values? Interviewer, yes, that's correct. Candidate, what is the ID length requirement? Interviewer, ID should fit into 64 bits. Candidate, what is the scale of the system that we are seeking in for this design? The system should be able to generate 10,000 IDs per second. Okay. So like these are the set of questions that can be put up by candidate to the interviewer to understand the problem. And it is important to understand the requirements and clarify ambiguities before proceeding further. So based on the question and answers, we have come up with certain requirements that we can jot down, and those are ID must be unique and should be numerical. ID should fit into 64 bits. IDs are ordered by date and time, and the ID generation process should be able to produce over 10,000 unique IDs per second. Yeah, so that is pretty much on the step one of understanding the problem, where we started by asking the question and then just laying down the requirements based on the answers and based on the understanding we got from the interviewer. Posing high level design and getting feedback on that. So in this part, we will try to propose a high level design for our unique ID generator, and we'll try to get a feedback of interviewer on it. So there are multiple options that can be used to generate a unique ID or unique IDs in a distributed system. The options that we will one by one see those multiple options, try to discuss them in detail. So we can start with multi-master application. So multi-master application approach uses the database auto increment feature to achieve the goal of generating unique IDs. So in this, instead of increasing the next ID by one, we increase it by k, where k is the number of databases in database server in use. So as shown in the diagram, next ID to generate is equal to the previous ID in the same server plus 2. Since you see we have two MySQL servers, that's why we are always incrementing by 2. Like here for generating IDs for the first server, we add 1 plus 2, 2 to each IDs. And so we made 1 plus 2, 3, and then 3 plus 2, 5. So in this way, we would generate the IDs for first server. And the second server also we started from 2 and keep on adding 2 to it. So like say 2 plus 2, a second ID would be 4, and then 4 plus 2, the third ID would be 6, and then 6 plus 2, 8. So in this way, we will keep on generating IDs. So here the k is the number of servers, which is 2 is in our case. So basically, we will increment our IDs by k or by 2 in this example. So this solves some scalability issue because IDs can scale with the number of database server. However, this strategy has some major drawbacks as it is hard to scale with multiple data centers. When we have multiple data centers, then this can be a problem. And IDs do not go up with time across multiple servers. And it does not scale well when the server is added or removed. So suppose server is added or removed, right? Then the ideally the k value will increase. But if the k value will increase, then how will we manage that in between the running of other servers also? So this adding and deletion of servers dynamically is also a challenge when we are going with this approach. So that is pretty much on the multi-master application approach. So in this part, we will talk about UUID. So UUID is another easy way to obtain unique IDs. UUID is a 128-bit number and it is used to identify information in computer systems. UUID has a very low probability of getting collision as defined after generating 1 billion UUIDs every second for approximately 100 years. There would be a probability of creating a single duplicate to each 50%. Like there's only a probability of 50% to each a duplicate only after generating 1 billion UUIDs every second for approximately 100 years. So the probability is very less if we talk about here. So an example of a UUID could be like the keys or the IDs that we generally saw, like that 09C93 -50B4 -468D so on. There can be lots of alphanumeric characters. So in this way, how a typical UUID looks. So UUIDs can be generated independently without the coordination between the servers as as we can see in this diagram. In this design, basically each web server contains an ID generator. Like we see it, we have these 4 web servers, and each web server contains an ID generator. And a web server is responsible for generating IDs independently. Like each web server can independently generate their own IDs. There's no synchronization or no handshake is required between them to generate these IDs. So in this way, we can use UUIDs to generate unique IDs for our system design. The pros of or the benefits of this approach are generating UUID is simple. No coordination between the server is needed, so there will not be any synchronization issue when we are using this. Then the second pro is the system is easy to scale because each web server is responsible for generating IDs they consume. So ID generator can easily scale with the web servers. Like each ID generation is independent in each web server, right? So it is very easy to scale to multiple servers also. Then few cons of this approach are IDs are 128-bit long, but our requirement is to have only 64-bit IDs, right? So that is a problem here. And IDs do not go up with time. Like IDs remain constant. Like there's no relation of IDs with the time. Time is independent. Like ID generated later in the time can be alphanumerically or lexicographically before the ID generated in the previous one or previous time or in past. There's no time correlation between the ID and the time. Then the last point is IDs could be non-numeric too. Like we see alphanumeric ones, right? So IDs could be non-numeric too. So that is pretty much on the UUID part. Ticket server. In this part, we will talk about ticket server. Ticket server is one more way to generate unique IDs. Flickr developed this ticket server to generate distributed primary keys. It's worth mentioning here like how the system works. So we have a ticket server and we have multiple web servers. Like in the diagram, we can see 4 web server and a single ticket server. So the idea here is to centralize auto increment feature in a single database server called as ticket server. And then basically this ticket server will there would be just a single server to basically handle this whole ID generation, where basically we will auto increment the IDs in the single database or single ticket server, and then all the web servers can consume or get the IDs from this ticket server. So in this way we work. If you want to know more about its inner working, then you can refer to the Flickr engineering blog attached to this course. So the pros of this method is like it gives us numeric IDs since we are going with that auto increment approach, and it is easy to implement, and it works for small to medium scale applications as we have a separate server for ID generation. So there's not it is easy to scale in comparison to the initial method that we saw of multi master replication thing. Since we can easily add or remove servers here without affecting the ID generation logic. A few cons of this approach are there is a single point of failure. Like there is a single server which is generating the ID. So if that server goes down, then all our IDs or all our account get lost. So there is a single point of failure. Single ticket server means to avoid a single point of failure, we can set up multiple ticket servers. However, this will introduce new challenges such as data synchronization also. That is a problem here. So that is pretty much on the ticket server. Twitter Snowflake. In this part, we will be talking about Twitter Snowflake way of generating unique IDs for a unique ID generator. So far we have seen couple of approaches to generate unique IDs, but none of them has met our specific requirements that we need for designing this system. So therefore, there is a need of some other approach to basically solve our problem. So Twitter unique ID generation system also called as Snowflake is an inspiring and can satisfy our requirements. So it works on a divide and conquer approach. So instead of generating IDs directly, in this we divide an ID into different sections. So in the diagram we can see our ID is being divided into different sections. To start with, there is a 1 bit in the start. To start with, there is a 0, which is a 1 bit in start, and then the 41 bits are allocated to timestamp, and then 5 bits are allocated to data center ID, and then 5 bits are allocated to machine ID, and then 12 bits are allocated to sequence number. So if we try to explain each section, then the first section is the sign bit, which is a 1 bit, and it will always be 0, and this is reserved for future use cases, and it can potentially be used to distinguish between a signed and unsigned numbers. Then the second section, timestamp. In this we use milliseconds since the epoch or a custom epoch. So we use Twitter Snowflake default epoch time, which is equivalent to November 04 2010. So basically timestamp denotes a epoch time that we use to display in this 41 bits of timestamp. And then in the data center ID section, there are 5 bits, which gives us 2^5 or 32 data centers IDs that we can specify here. Then the fourth is the machine ID, where again it is 2^35 or 32 machines per data centers. We can have the machine IDs of that here. And the last is the sequence number. The sequence number is a 12-bit sequence, and for every ID generated on the machine or process, the sequence number is incremented by 1. Here we follow that auto increment logic, and the number is reset to 0 every milliseconds. So basically, for every ID generated on the machine or process, the sequence number is incremented by 1, and the number is reset to 0 every millisecond. So in this way, sequence number works. So pretty much we can use these sections to generate a unique ID for us, where we can, here we have also the advantage of this approach is like we have also included a timestamp here. So ID generated in future will have a more timestamp, a more number than the ID generated in past. And we have also included that auto increment for, functionality using that sequence number. And we are also getting here data center ID and machine ID. And to handle signed and unsigned bit, there's also an initial 1 bit reserved for that. With the help of this, it gives us lots of flexibility to generate a unique ID for our use case. So mostly we will be using this, so in our system design, we will be using this Twitter Snowflake way to generate unique IDs for our system. So that is pretty much on the Twitter Snowflake unique ID generation part. And with this, we complete our proposing our high level design and proposing a way to generate a unique ID to interviewer and getting his feedback. Now, in the next step, we will try to deep dive in our design. In this part, we will try to deep dive in our design. So in previous step, we proposed our high level design and we discussed various options to design a unique ID generator in a distributed system. And finally, we settle on an approach that is based on the Twitter Snowflake ID generator. So let's just now deep dive into the design and to express our memory. Here is how a Twitter Snowflake unique ID looks. It has initial unsigned or signed bit, then a timestamp 41 bits, then 5 bits for data center ID, and then 5 bits for machine ID, and then 12 bits for sequence number. So the data center IDs and machine IDs are chosen at the startup time and generally fixed once the system is up and running. Any changes in the data center IDs and the machine IDs require careful review, careful review, since an accidental change in those value can lead to ID conflicts. Timestamp and sequence numbers are generated when ID generator is running. Now, talking about the timestamp, the most important 41 bits that we see in the unique ID generator of Snowflake. In this, the most important 41 bits make up the timestamp section. A timestamp go with time. IDs are sortable. So our timestamps go with a time and IDs are sortable by time too. So as we can see is in this diagram, it shows how an example of how binary representation is converted to UTC. So this is a binary representation that we see. And when it is converted to decimal, it looks like this. And then we add with a epoch, basically that starting time of this to this, and then we get this number. So this is, and if we convert this milliseconds to UTC time, then this will look like this. This would be our UTC time like April 9, 2020, 1651. So basically from the decimal numbers that we got, we can generate our UTC time out of that, UTC timestamp out of that. And the maximum timestamp that can be represented in 41 bits of timestamp is 2 to the power 41 minus 1, which is 219902325 55551 milliseconds, which gives us 69 years. And if we divide this big number by 1000 seconds, by 365 days, by 24 hours, so basically it will come up around 69 years. The maximum timestamp that can be allowed in this via this 41 bits of timestamp is 69 years. And so in a way we can say the ID, this means our ID generator will work for 69 years and having a custom epoch time close to today's date delays the overflow time. And after 69 years, we will need a new epoch time or adopt other techniques to migrate IDs. So this is a thing in the timestamp. Then one more thing to consider here is the sequence number in our Snowflake ID generated ID. Then that is the last part, sequence number. The sequence number is of 12 bits, which gives us 2 to the power 12, or basically 4096 combinations. And the field 0 is unless more than one ID is generated. This field remains 0 unless more than one ID is generated in a millisecond on the same server. In theory, a machine can support maximum 4096 new IDs per milliseconds. So basically, this field remains 0 unless there is more than one ID generated in that particular millisecond on the same server. And in the theory, a machine can support maximum of 4096 new IDs per millisecond per server. That is quite a large number. So in this way, sequence number can also help us to add uniqueness to our ID. So that is pretty much ongoing deep dive on our Snowflake ID generator and seeing how it works internally and how it can help us to generate unique ID. So in this part, we will try to wrap up things. So basically in this section, we discuss different approaches to design unique ID generators. One was Multi Master Replication, then there was UUID, then Ticket Server, and at last it was Twitter Snowflake like unique ID generator. And we finally settle on Snowflake as it supports all our use cases and is scalable in a distributed environment. Okay, so if I summarize, we can say we discussed a couple of approaches, right, that we saw. And after considering all the options, we decided to settle on Twitter Snowflake like unique ID generator. And this decision was based on the fact that the Snowflake generator is capable of supporting all our use cases and is also a scalable in a distributed environment. So some additional points to call out here, like interviewer can also ask us some additional talking points that we can suggest him is clock synchronization is assumed in our ID generation design, but this assumption may not hold true for servers running on a multiple cores or multiple machine scenarios. Solutions such as network time protocol exist for this if he wants to address that use case. Then section length tuning is important and can be adjusted depending upon the application requirements. So fewer sequence numbers, but more timestamp bits may be affected for low concurrency and long-term applications. So like if we are here, we are talking about a fewer sequence numbers in our Snowflake ID, but more timestamp bits may be effective for low concurrency and the long-term applications. And then high availability is crucial for our mission critical systems like ID generator. So it should be designed to ensure high availability at all times. Like our systems should be designed in a way so that it can ensure high availability. So that is the things that we can highlight or we can talk about if interview asks also. So yeah, that is pretty much on designing a unique ID generator. So yeah, thanks a lot.